Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will see next unit, normal subgroups and its properties. Let us consider first the definition of normal subgroup. We have studied groups, subgroups in last year. Definition of normal subgroup is a subgroup H of a group G is said to be normal subgroup of G if for all G belongs to G and for all H belongs to H, G inverse belongs to H. That means here G is a group, H is subgroup of G, then a subgroup H of a group G is said to be normal subgroup of G if for all G belongs to G and for all H belongs to H, G inverse belongs to H. For objective question, one can be asked as a subgroup H of a group G is said to be normal if dash dash. It is G inverse belongs to H. Now consider some remarks. Number one remark is H is a normal subgroup of G if for all G belongs to G and for all H belongs to H, G inverse belongs to H. H is normal subgroup of G, then for all H belongs to H and all G belongs to G, G inverse belongs to H. Second remark is a normal subgroup is also called invariant or self-conjugate subgroup. This is another names for normal subgroup. That is invariant or self-conjugate subgroup. Third remark is every group G possesses at least two normal subgroups, namely G itself and singleton E. That means every group G possesses at least two subgroups. One subgroup is G itself and other is identity element, where E is the identity element of G. These are called as trivial or improper normal subgroups of G. Now we consider one example. If G is a quaternion group and H equal to 1 minus 1 is a subgroup of G, then H is a normal subgroup of G. Here G is quaternion, G equal to 1 minus 1 I minus I, and H is subgroup. That means H equal to 1 and minus 1. Only two elements are there. H is subgroup of G. Then G is H equal to 1 minus 1. Then H is a normal subgroup of G. That means G inverse belongs to H. G inverse belongs to H. Now we consider one definition, that is definition of simple group. A group having no proper normal subgroups is known as a simple group. In above example, if G is quaternion group and H is subgroup of G, GHG inverse of 1 is 1. 1 into 1 or 1 into minus 1 into 1 equal to minus 1. It belongs to H. Also for 1, minus 1, 1, getting GHG inverse belongs to H. That is for 1. 1 into 1 is 1. 2 inverse of 1 is 1 belongs to, that is 1 belongs to H. Also take minus 1. Minus 1 into H into minus 1 inverse is minus 1. Belongs to minus 1 into minus 1, that is 1 belongs to H. Also you can take minus 1. 1 into minus 1 into 1, that is minus 1 belongs to H. So that this property is satisfied. Now we consider one theorem. Statement of this theorem is a subgroup H of a group G is normal if and only if GHG inverse equal to H for all G belongs to G. Let us consider the proof of this theorem. Here we assume that H be a normal subgroup of G. Then from first remark, that is if H is a normal subgroup of G, then GHG inverse belongs to H, where H is subgroup of G. So that GHG inverse is contained in H for all G belongs to G. Let us denote this term as 1. Also G belongs to G. This implies G inverse belongs to G. Therefore, from 1 we have G inverse into H into G inverse is contained in H. That means instead of G is replaced by G inverse. This implies G inverse into H, G inverse is G, is contained in H for all G belongs to G. And this implies G, that means multiply both left and right by G and G inverse. This implies G into bracket G inverse HG bracket complete into G inverse is contained in GHG inverse for all G belongs to G. This implies G into G inverse is 1. G into G inverse is 1. H is contained in GHG inverse for all G belongs to G. Denote this as number 2. From 1 and 2, we conclude that GHG inverse equal to H for all G belongs to G. Conversely, let GHG inverse equal to H for all G belongs to G. Then clearly then clearly GHG inverse is contained in H for all G belongs to G. Hence, H is a normal subgroup of G by definition, since GHG inverse belongs to, is contained in H or belongs to H. Thus, in this case, we have proved the theorem. Now we consider another theorem. Theorem 2. Statement of this theorem is a subgroup H of a group G is normal if and only if every right coset of H in G is a left coset of H in G. That means GH equal to HG. Let us consider the proof of this theorem. Let H be a normal subgroup of G. Then by theorem 1, if H is normal, then GH inverse is contained in H or equal to H for all G belongs to G. This implies GHG inverse into G equal to H into G, that is multiplying both sides by G on right. This implies GH into G inverse into G equal to HG by associative property. This implies GH into G inverse into G is H equal to HG, and E is identity element, so that this implies GH equal to HG. That means commutative property is satisfied, that is every right coset of H is equal to left coset of H. Hence, every right coset of H in G is a left coset of H in G. Now conversely, suppose that means here first we assume that H is normal subgroup of G, and we have proved that every right coset of H in G is equal to left coset of H in G. Conversely, suppose that every right coset of H in G is a left coset of H in G. Then, for any G belongs to G, GH equal to HG. That means every right coset equal to left coset, GH equal to HG. This implies GHG inverse equal to HG into G inverse. This implies GHG inverse equal to H into G inverse in bracket. In bracket G into G inverse bracket complete by associative property. This implies GHG inverse equal to H into E, since G into G inverse equal to identity element E. This implies GHG inverse equal to H, since H equal to H is an identity element. Thus, if every right coset of H in G is a left coset of H in G, that means if HG equal to GH or GH equal to HG, then GHG inverse equal to H or GHG inverse is contained in G. That means H is normal subgroup of G. Hence, we have proved the theorem in both the parts. That means a subgroup H of a group G is normal if and only if every right coset of H in G is a left coset of H in G. If and only if part. So that we have proved this theorem in two parts. First, we assume that H is normal subgroup, and we prove that every right coset equal to every left coset of H in G. And in second part, we have assumed that every right coset of H in G is a left coset of H in G, then H is normal. Thus, we have proved the theorem. Thank you.